All right, here's some hints to help you get started on the chapter 16 through 18 assignment. There are quite a few problems, and this isn't on all of the problems, but I'll give you hints anyway, and maybe this will help. Problem number 54 on the chapter 16 assignment. Light is traveling from the moon to the earth. And since light travels a constant velocity, you probably would be advised to use the velocity equals distance divided by time formula. Well, let's jump over to problem number 59. It's a simple conversion. You'll need to do that multiple times in the next few chapters. So just recognize that the the best conversion regarding nanometers is that 1 meter is 1 times 10 to the 9th nanometers. So in other words, a nanometer is very small. It's a billionth of a meter. And there you go. Jumping over to the next assignment, page 479 to 481, let's look at number 54. In number 54, a beam of light is hitting a mirror. And I will advise during this entire unit, draw lots of diagrams. That's going to be very important. So your mirror, we're looking down on the mirror. A beam of light, as I've indicated in red, is arriving. Now what I love to do is draw the normal as perpendicular to the boundary. So perpendicular to the boundary, there is this normal and it continues beyond the mirror. And so what we do is measure the angle of incidence, and then the angle of reflection will be the same. So hopefully that'll help you on number 54. And we'll look at number 60 now. Number 60 is kind of a crucial problem. And that's because you have kind of an adjustment that is needed. The angle of incidence is defined as the angle between the light ray and the normal. Well, if you look at number 60, you're going to rotate the mirror. Of course, rotating the mirror rotates the normal 18 degrees. So what happens is the light ray stays in the same place, but the normal is rotating 18 degrees closer to the light ray. Well, that means that the angle of incidence is 18 degrees less than it was. Now, this is a little bit of a trick question. When they're finished with this question, they ask you to find the angle between the light ray and the mirror. Remember, the angle of incidence and reflection is between the light ray and the normal. And let's jump another page. Number 61, and if you look at number 61, it has to do with curved mirrors. And remember, curved mirrors are typically not parabolas, but half a circle or a part of a circle. So the focal length is half of the center of curvature. For number 66, we have our standard and an important standard curved mirror. They give you the height of the object, that's 3.8. They give you the focal length, that's 16. They give you the distance from the mirror to the object as 31 centimeters. So the formula for the lens maker's formula is 1 over the focal length equals 1 over di plus 1 over do. After you use that, then you can use the other magnification formula, which is di over do equals the opposite of hi over ho for number 61, or number 66. Number 67 is more practice of the same formula, lens maker's formula, 1 over di plus 1 over do equals 1 over f. Okay, number 70 is the same formula, but the interesting thing is they tell you the center of curvature, but they don't tell you the focal length. Well, you simply have to take half of that to get the focal length. Then you're back to the very same formula we just used. And that leads us to number 72. So number 72, you're going to be drawing a diagram. And when you draw a diagram, you're going to follow 2 rays of light. Now, what I'd advise is you follow the 2 rays of light, one that goes parallel to the axis of symmetry. So this ray of light that goes parallel, it is forced to reflect through the focal point and continues on toward your eye. Okay? Then you're going to follow one more ray of light, the ray of light that goes through the axis of symmetry, and then what it does is it has to do the reverse and goes out parallel to the axis of symmetry. Now, where those two meet up, the place where those two join is just like they were joined originally at the object, they will join up at the image. There's where the image is. And then, beyond that, it's the same formulas we've been using all along, where they give you the focal length, the distance from the object to the mirror, and the height of the object to solve the rest. So this is, I think, a good start for that one. Number 67 of page 509. Again, you really should draw diagrams for these. So number 67, you're going to use Snell's law. N1 sine of I equals N2 sine of R. Number 70, it'll help you to recall that the index of refraction is C over V. Remember, this is the index of refraction that tells you how much something bends the light. C is the speed of light in a vacuum, and V is the speed of light in a particular material. Number 71, the sine of the critical angle is N2 over N1. Remember, N2 is where the light is trying to go, and that always with this formula will be a small number, whereas N1 is where it starts, and a very large number. Number 74, we are going to use Snell's law twice. Number 75, use N equals C over V 2 times. Now there's a tougher question in number 76, and so here is a little bit of a hint. First, I would recommend that you use the sine of the critical angle as N2 divided by N1 to start the problem out. Now in this case, the beginning has an N2 for air of 1.0008. Solve for the index of the kind of glass that they have, and every glass has a different index. Then use the critical angle formula, which is N2 over N1, but this time it's immersed in water, the N2 of water, which can be looked up by you, or is 1.33. Number 79, again, you're getting used to this formula. The index is C divided by V. That helps you to find the index for a particular kind of plastic. Well, then you could use Snell's law now that you know what the index of refraction is. And coming down to one of the tougher questions, and the last one I want to help you with, is this one, where the beam of light is arriving at 45 degrees, and we want to see where it will leave. Well, again, this is the normal. What I draw is the light going in a straight line. It's not going to do that. Instead, what it's going to do is change direction. Okay? So when it goes into a material, it's going to change direction, and that will be toward the normal. That's closer to the normal. What you should do is use Snell's law to find that angle, make a brand new normal right there, and use geometry to figure out what this new angle of incidence is, to see if it's beyond the critical angle or not. I hope this really helps. Thank you.